You ever wonder about the invisible forces that are just all around us? You know, that little spark you get when you touch a doorknob? Or why a balloon, after you rub it on your head, suddenly seems to defy gravity? Well, today, we're going to decode one of nature's most basic and most powerful secrets. And believe it or not, it all kicks off with a simple classroom experiment. So let's set the scene. We're in a physics lab with a student named Arav. He takes a balloon, rubs it on his hair, and poof, his hair stands right on end. Then he realizes that same balloon can pick up little bits of paper. Now, it looks like a magic trick, right? But what he's actually seeing is his first clue into one of the fundamental forces of the entire universe. So what was actually happening there with Arav's balloon? He had just, completely by accident, tapped into the concept of electric charge. And that is the very foundation of what we call electrostatics. To get this, we gotta zoom way in. See, everything is made of atoms, and atoms have positively charged protons and negatively charged electrons. Usually, everything's perfectly balanced, but when Arav rubbed that balloon on his hair, electrons literally leaped from his hair onto the balloon. That one simple action gave the balloon a negative charge and created this crucial imbalance. And that imbalance, that's what this is all about. Electrostatics is just the science of these charges that are sitting still, or static, and the invisible forces they create all around them. You know when your clothes stick together coming out of the dryer? Yep, that's electrostatics at work in your laundry room. Okay, so we've got these separated charges, but how do they actually interact with each other, from a distance? Well, that question leads us straight to the fundamental rules of attraction and repulsion, and it's all wrapped up in something called Coulomb's law. The basic idea here is it's beautifully simple. If charges are the same, two positives or two negatives, they push each other away. But if they're opposites, a positive and a negative, they pull toward each other. It's like this invisible dance of forces that's happening constantly, all around us. And that's the next big question, isn't it? It's one thing to know that they attract or repel, but in physics, we want to measure things. So how can we figure out the exact strength of that push or that pull? Well, Coulomb's law gives us two really clear rules. First, the bigger the charge, the stronger the force. That kind of makes sense, right? But the second rule is fascinating. The force gets weaker really fast as the charges get farther apart. In fact, if you just double the distance between them, the force drops all the way down to 1/4 of what it was. And here it is, in all its mathematical glory. This awesome equation lets us calculate that force with total precision. See how the charges Q1 and Q2 are up top? That just means bigger charge equals bigger force. And see the distance, r, on the bottom, and it's squared? That's the math that explains why that force fades away so quickly. Now, hold on a second. If these charges can affect each other without touching, how do they do it? How does one charge even know another one is over there? The answer is an amazing concept, an invisible field of influence. Think of it like this. Every single charge creates this invisible zone of influence in the space around it. It's not empty space anymore, it's primed to exert a force. So the moment you bring a second charge into that electric field, it instantly feels that push or pull. The field is like the messenger between them. And to help us picture this invisible field, scientists draw what they call field lines. They follow a few simple rules. The lines always point away from positive charges and swoop in towards negative ones. And here's the real key. Wherever those lines are bunched up tightly together, that's where the electric field is the strongest. So building on this idea of a force field, let's talk energy. You know that feeling when you try to push two magnets together the wrong way? You have to fight against that repelling force? Well, the effort you put in, it gets stored as energy. In electricity, we call that stored energy potential energy. This whole idea is known as electric potential. It's basically just a way to measure how much potential energy a charge has simply because of where it is in an electric field. The more work you do to push a positive charge closer to another positive charge, the higher its electric potential gets. And this is where it all clicks. Arav asks this amazing question. Is voltage just the difference in electric potential between two spots? And the answer is yes, exactly. That 9-volt battery you have, it just means there's a 9-volt potential difference between its positive and negative terminals. It's that simple. Okay, so this all might sound a little abstract, but understanding these principles is, and I mean this literally, what allows us to build the entire modern world. So let's take a look at how we've actually learned to harness this incredible invisible force. One of the most basic, most important electronic parts is the capacitor, and its entire job is pure electrostatics. It's a device designed for one thing, to store up electric charge and, with it, electrical energy. The design is simple, but it's incredibly powerful. You've got two metal plates with a tiny gap between them. Charge builds up on those plates, which creates a voltage. But here's the really clever part. You can stick a special insulating material called a dielectric in that gap. And when you do that, you can suddenly pack way more charge into the same space, which boosts its storage capacity like crazy. And trust me, these little things are everywhere. You know that super bright instant burst of light from a camera flash? That's a capacitor dumping all of its stored energy in a split second. They're essential for the power supply in your computer, your phone, pretty much any piece of modern electronics you can think of. And the applications go so much bigger than just tiny circuits. The very same principles explain the raw power of a lightning bolt, which is really just a giant electrostatic discharge. They explain how photocopiers work, how big industrial smokestacks can use electrostatics to scrub pollution out of the air, and even how those crazy Van de Graaff generators in science museums make your hair stand on end. And that brings us right back to where we started. That simple experiment with a balloon and some hair, it ended up revealing a fundamental force that connects everything, from the atoms inside our bodies to the massive storms in our skies. What seemed like a simple bit of physics becomes a key to understanding the invisible architecture of our universe. So the next time you see a tiny spark of static, what hidden language will you see?